Hello everyone, my name is Christian McAuliffe. I am a senior chemical engineering major at Hampton University, and thanks to the MAOP SRI program, I have had the opportunity to conduct the research I am presenting today. So, let's get started. The effect of process parameters on the tensile properties of PLA and ABS parts generated by fused filament fabrication. Fused filament fabrication, also known as 3D printing, is a form of additive manufacturing. The polymer, in the form of a long strand of filament wound up on a roll, is fed into the machine by a set of rollers which grip and pull the filament tightly. The filament is passed through a heated nozzle, reducing it to a molten state before being deposited onto the bed to cool. The nozzle is situated upon a mobile gantry which possesses 3 axes of movement. This video illustrates the process. There are several parameters of the building process which fused filament fabrication machines allow users to control. Here is a list of the parameters relevant to this study. Infill describes the amount of polymer present in a part measured by a percentage. Print temperature is the temperature the nozzle, shown here, operates at. Bed temperature is the temperature of the print bed, shown here. Both temperatures are measured in degrees Celsius. Print speed is the speed at which filament is deposited in millimeters per second. This is controlled by the rollers here. Build orientation refers to the orientation of the part in relation to the print bed. For example, the part here is built in the XY plane at an angle of 0 degrees. Layer thickness is simply the thickness of each layer of polymer deposited, shown here. Raster angle describes the angle each layer is deposited at. A magnified view of 2 layers with opposing raster angles is shown here. So the question is, do these parameters have any impact upon the properties of parts generated by fused filament fabrication? And if so, which ones are most significant? For the purposes of this analysis, we will focus on how they impact the tensile strength of parts made from polylactic acid, or PLA. PLA was chosen for this presentation over ABS primarily because of its popularity among additive manufacturing fields. This is likely due to its lower melting point, making it easier to print. PLA is also more environmentally friendly than ABS, as it is sourced from starchy plants like sugarcane rather than petroleum. PLA's popularity leads to a greater amount of data concerning it in the literature, making the model featured in this study more accurate. A total of 30 reports were selected from the literature, and a dataset constructed from their results. The dataset was then organized into factors and levels, shown in the table to the right, to facilitate an analysis of variance or ANOVA test. ANOVA tests tell us which factors produce statistically significant differences in the response. In this case, the factors are build parameters, and the response is tensile strength. The following slides contain all the data organized in box plots. A box plot is a graphical summary of the relevant values of a dataset. The middle line indicates the median of the data, followed by the first and third quartiles and the maximum and minimum values. The black dots are outliers. This slide contains the plots for infill, print temperature, bed temperature, and print speed. This slide contains the plots for build orientation, layer thickness, and raster angle. Here we have the results of the ANOVA. The most important values to take from the table are the F value, highlighted in blue, and the P value, highlighted in purple. They are what determine the parameter significance. These values are tested against the null hypothesis, which states that all factor means are equal, meaning little to no correlation. An F value close to 1 and a P value greater than 0.05 indicate that the factor is not significant. As seen in the table, the F values for infill, print temperature, bed temperature, and build orientation are very high, with raster angle showing a lower but still significant F value. In addition, these parameters all possess minuscule p-values. This allows us to reject the null hypothesis for these parameters and conclude that they have some significant impact upon part tensile strength. However, the parameters print speed and layer thickness have f-values very close to 1, along with p-values above 0.05, indicating that these parameters have no significant impact upon part tensile strength. The results of the ANOVA analysis show us that the important parameters to consider when optimizing parts for tensile strength are infill, print and bed temperature, build orientation, and raster angle, while print speed and layer thickness are insignificant. Based upon the reports in the literature, I hypothesize that this is due to the large impact of infill, build orientation, print temperature, and bed temperature. When compared to these major parameters, print speed and layer thickness may only appear insignificant. The next steps for this analysis will be to gather more data to increase the accuracy of the model, along with post hoc tests, such as the Tukey multiple comparison test, to determine which levels of these parameters produce the strongest parts, and are print speed and layer thickness only insignificant in relation to the other parameters. I would like to again thank the MAOP undergraduate SRI program for providing this opportunity. I would also like to thank the Bortner Lab Group, specifically Dr. Michael Bortner and Arit Das, whose assistance was integral in this study. Finally, I would like to thank Rapid Prototyping Journal, as they published a majority of the reports utilized in this study.